Solutions. A solution is a homogeneous mixture that has at least one solute, which is the substance of lesser quantity, and one solvent, a substance of greater quantity. Homogeneous means when you look at it, you only see one type of particle. It all looks uniform. And a solute is the substance that is there in smaller quantities, but it is the substance that is dissolved. The solvent is the substance that's there in larger quantities, and it is the substance doing the dissolving. Normally, we use water as the solvent. Solutions can be colored or colorless, but they all have only one phase. That's that uniform appearance. Solutions come in many combinations of state. For example, a common gas in gas solution is the air around us. The biggest component of air is nitrogen gas. So basically, nitrogen gas would be considered the solvent. The gasoline that we put in our car is a liquid-liquid solution of more than 400 different hydrocarbons. So you can have whatever the largest volume is for your mixture, that would be the solvent. You can also have solid-solid solutions. An example of that is stainless steel. You look at the stainless steel tap in your sink. It's uniform in appearance. It's got that silver color to it, but it's an alloy. It is a mixture of different metals and sometimes even carbon. Aqueous solutions are made from solutes dissolved in water. Water is considered to be the universal solvent because it dissolves more substances than any other solvent. And when we have an aqueous solution, we indicate that with the AQ subscript. So if an aqueous solution conducts electricity, the solute is considered an electrolyte. If it does not conduct electricity, the solute is a non-electrolyte. Examples of electrolytes are soluble ionic compounds and bases. Non-electrolytes are covalent compounds with the exceptions of acids, and that's because acids ionize and produce ions, so they would fall under the general electrolyte grouping. When you drink an energy drink because you've just played a game of basketball or hockey, you have electrolytes in it to replace electrolytes in your body, such as salt ions and potassium ions. And that's why it's a little bit salty sometimes. The sugar that's added is added for the energy, to give you an energy boost. So an energy drink contains sugars for energy, and then salts to replace the salt that's leaving your body when you sweat. To identify a solution as molecular or covalent, ionic, acid or base, a couple of tests can be run. So if you have an unknown solution, you can test the conductivity, and it's either going to conduct electricity, which indicates that it's an electrolyte, or it's not going to conduct electricity, in which case it's a non-electrolyte. So if you test a solution and it doesn't conduct, then you know it's a molecular or covalent compound. If it does conduct electricity, then you have to do one more test and test the pH. If it's below 7, it's acidic. If it is 7, it's neutral, so it's an ionic compound. And if it's above 7, it's basic. And these can be, so bases are ionic compounds also, but you'll know them by the formula ending in OH, hydroxides. Just a little bit of terminology. Acids will ionize. They're covalently bonded, but they will form ions. So we say they ionize. whereas ionic compounds dissociate. They are ions bonded together, so when you dissolve them, they dissociate into their ions because they were already ions. So acids ionize because they're covalently bonded initially. Ionic compounds dissociate because they are ions already bonded together. Litmus paper test for pH, just for a quick review. For an acid, positive test is your blue litmus paper turns red, and for the base, red litmus paper turns blue. Review of intermolecular forces. So intermolecular forces are forces of attraction between molecules. So these exist only between covalent compounds. Intramolecular means within a compound. So those would be bonds inside. So water, H2O, has two HO bonds. Those are intramolecular. But intermolecular forces are between molecules of water. So you've got your weak van der Waals forces, and these are your London dispersion and dipole-dipole forces. LDS, or London dispersion forces, basically if you have an electron, you will have London dispersion force. It's the attraction between the negative electrons and the positive nucleus in a neighboring molecule. It exists between all covalently bonded molecules and even between atoms of noble gases. Dipole-dipole forces is an attractive force acting between the oppositely charged ends of polar molecule. So if you have a polar molecule, you've got a positive end and a negative end. The positive end in one is attracted to the negative end of a neighboring molecule. Hydrogen bonding. So this is the special case of relatively strong dipole-dipole force between a slightly positive H atom in one molecule and the very electronegative atom in a neighboring molecule. However, there's a caveat here. The hydrogen atom must be attached to an oxygen, nitrogen, or fluorine atom for this to happen. So that slightly positive H is attached to an oxygen, nitrogen, or fluorine. So this molecule can have hydrogen bonding, and it's between this H in the bottom right and the fluorine atom. You have to be bonded. If you had, let's say, SH and an SH2, so you've got two molecules of SH2 or H2S. There's no hydrogen bonding here because this is not nitrogen, oxygen, or fluorine. So no hydrogen bonding. This one has hydrogen bonding. Okay, molecular or covalent compounds in water. Water is a very polar molecule, and it contains these very polar OH bonds. So it's able to dissolve. Its ability to dissolve is related to the fact it can form hydrogen bonds with solutes. If there's more than one site to make hydrogen bonds with your solute, it will be very soluble. When a polar molecular substance dissolves in water, it will disperse electrically neutral particles evenly through the solution, and electricity will not be able to flow. So sucrose particles sucrose is a polar covalent molecule, and it will get surrounded by water molecules. So that's basically how it dissolves. There's hydrogen bonding between the water molecules and the sucrose molecules. Ionic compounds in water. When an ionic compound dissolves in water, they will dissociate or break up into individual aqueous ions. The positive ions are surrounded by the negative dipoles in water, so closer to the oxygens, and the negative ions from the compound are surrounded by the positive dipole in water molecules. For example, sodium chloride. So if you have a sodium ion, that's positive, so it's going to be surrounded by the slightly negative oxygen. So just imagine that that goes all the way around, and then the chloride, which is negative, will be surrounded by the slightly positive H's. So just pretend that that also goes all the way around. So that's basically what happens. Your ions get surrounded by water molecules. Nonpolar solutes. So nonpolar solutes can be dissolved in nonpolar solvents because the weak intermolecular forces that attract solute molecules to each other and the solvent molecules to each other are easily overcome by the continuous random motion of the particles, allowing them to mix and become a solution. Most covalent compounds are polar, but if you have something that doesn't dissolve in water, let's say you get grease on a shirt or grease on a pair of pants, water won't get it out alone because water is polar. What you could use is something that is nonpolar, like hexane or kerosene, because the nonpolar solute will be dissolved by the nonpolar solvent. So you've got to remember when you're dissolving that like dissolves like. Polar molecules will dissolve in polar liquids or substances. Nonpolar substances can be dissolved in nonpolar solvents. Some nonpolar solutes can dissolve in polar solvents if they're small. Otherwise, they don't dissolve at all. Now, when you write a dissolving chemical equation, there is a certain way to do it. So let's say we have glucose, C6H12O6 solid. So this is the dissolving of a covalent solid. You would write C6H12O6AQ. You do not put water into your chemical equation because it's not reacting with water. It's simply being dissolved by water. Dissolving is a physical change, not a chemical change. So it goes from a solid to an AQ. If you have an ionic compound, for instance, sodium chloride, there's two ways you can write it. It becomes aqueous sodium chloride. So you write it the same way. The only difference is the subscript. Or you can write it as its ions. And those are AQ. For a substance like calcium chloride, you've got to be careful that you write the correct ion when you do this. So calcium forms a 2+ ion. Chloride is still Cl -1. That's the true ionic formula for chloride because it only receives one extra electron, but there are two of them. So it gets a coefficient of 2. So you have to be careful when you have multiple ions in your formula.